which we can do the multi-level logic optimization. So we come across the elimination method. So given a set of functions, we would try to explore how we can use the previously computed function to compute the current function. For example, over here you can see this z equals to a complement x or cy, but these x and y have been computed before. So there is no need to externally provide these inputs x, y. So we will reuse these functions over there. So naturally, if I put b or c for x and a or b for y, then I convert it into an SOP expression, and after minimization it comes down to z equals to a complement b or c. So it just becomes a function of a, b and c only, and I eliminate x and y from the expression. So both from the number of variables point of view as well as the gate count point of view, you can see a reduction. So this is a 4 variable Boolean function, and so over here we can see that you have transformed the 4 variable Boolean function into a 3 variable Boolean function. So the elimination process can begin with any number of Boolean functions, and finally you come down to a Boolean function with reduced gate count as well as reduced number of variables in the Boolean function. So particularly for devices such as FPGA, where you are computing so many Boolean functions together, you can find out how you can reuse the existing Boolean functions to optimally compute the functions under consideration. Next we go into the substitution method. So in case of substitution, we try to find out the commonalities between parts of a Boolean expression. So over here you see this function h equals to a and c complement or d complement and e or f plus b c d e complement f complement. Over here you see that c complement or d complement is the complement of c d, and e or f is the has a complement e complement f complement if you apply De Morgan's law. So now you put x equals to c d and y equals to e or f. So you get x complement equals to c or c complement or d complement, and y equals to e complement or f complement. And now you substitute x for c d and y for e f. So you get the expression as h equals to a x complement y plus b x y complement, and if you put the values of x and y, the total gate count still gets reduced from 14 to gate input cost gets reduced from 14 to 12. Now so this is an approach where you see that whether you are using some sub expression at multiple places or not. If you are using the same sub expression at multiple places, then you try to compute it separately and provide the output of that sub expression to the inputs at multiple places where you are using the sub expression. Okay? Yes. Huh? No, this plus this plus this, because you are using x and y also over there. That is why I have written at the bottom That is why I have written at the bottom, right. Coming to extraction, so suppose we are given two functions e equals to ABD plus ABD complement and H equals to BCD or BCD complement. You can see that BD or BD complement is common to both the functions. So, I should not compute separately BD or BD complement in both the functions. I should compute it once and provide it as input to both the functions. So, I am finding the common factor for E and H and then define the common factor as a function and then perform extraction by expressing E and H as a function of F. The gate count thereby gate input cost thereby gets reduced substantially. You can see a decrease in the gate input cost from 16 to 10. So, because I am sharing this function f over E and H, so that is basically the trick. I am reducing the gate input cost. So, what we understand from all these techniques, we have studied a couple of techniques in the last class and also few more techniques in this class. We understand that we have to find, depending upon the problem, we have to find avenues for finding commonalities of sub expression in multiple expressions, or wherever possible we can even shrink down the expression using the laws of Boolean algebra or using substituting some sub expression with some Boolean variable and using that sub expression at multiple places. So, there are different, so altogether we have learned multiple techniques by which we can reuse sub expressions at multiple places or minimize the size of Boolean expression to minimize the number of literals as well as the gate input cost. So, given a Boolean function, you have to explore how to further how to operate on it and minimize the Boolean function optimal for implementation on a given array architecture. Okay. So, regarding the regarding your lab, so tomorrow you have to finish the assignment on the processors. I already told you to, if you can do, you can finish a large part of it at home also if you wish. So, tomorrow is the last date for the processors assignment, and the next assignment will be somewhat of a project kind, which comprises of this hardware software co-design. So, that will again span over 2 classes, plus you can if you wish to do it in extra time at home or whatever, you can do it. That is on 8th and 15th, and on 17th November, that is Sunday, you will have your lab examination. So, the lab examination will take place for 6 hours with 3 hours of microcontroller based problem to be solved and 3 hours of FPGA VHDL based problem to be solved. Okay. So, the lab examination, I want to finish it before the actual examination starts. So, we will have it on 17th of November. And so, before the lab examination, please ensure that you have got all your reports checked, evaluated, and all your assignments evaluated. If something is left, please do it before that. Regarding this, the next assignment, that is the assignment on hardware software co-design. If you recall, we said that initially that the project will have a weightage of 10% of the total weightage of the course. So, the next assignment, that is the assignment on the hardware software co-design, which is a very important assignment so far as the embedded hardware design course is concerned. It will bear 10% of the total weightage for the EHD course. Okay. Now, regarding the class discussions, are you all following the class lectures? Yes or no? Yeah. Which? No, but multiplier, you can look it as a process of repetitive addition. You can, by now you know what is multiplication. At least I am not expecting you to implement multiplier using a compressor architecture or using a Wallace tree architecture, whatever, but you can at least use a sequence of half adders and full adders to implement your multiplier. That is possible, that you can do. I thought at least so far as the array multiplier is concerned, an array multiplier we have already done in the first assignment on VHDL, if you recall. Huh? Serial bit multiplier. Yeah. Yeah. But serial multiplier you haven't done in DLP? But that is also not that difficult also. So far as circuits like encoder, decoder, multiplexer, register, flip-flop, these things are concerned, there is always a clear picture of whether something is covered in a course or not. So far as things like variations of adders, variations of multipliers are concerned, it is of course left to a course teacher to decide whether he will teach or not teach that specific topic. So I cannot comment on that, but so far as for example this encoder is concerned, there are lots of variations of encoder. For example, the priority encoder, because I while teaching this flash ADC came to I came to know that that was not being covered, priority encoder, so I taught that. So so this kind of local variations, it is ultimately left to a course teacher to decide whether he will cover or not cover, depending upon the availability time and all that. So as I said that one of our emphasis in embedded hardware design course would be how to interface the embedded core with the different peripherals, and so again we come back to our earlier discussions on how to interface the microcontroller or FPGA whatever with the peripherals, and one of the possible ways by which we do the peripheral interfacing is by the serial peripheral interface or SPI. So see, the serial peripheral interface is basically a simple protocol by which you can connect any number of devices, peripheral devices with the controller. So we will discuss on this what is the serial peripheral interface. We will see the basic architecture for the serial peripheral interface or SPI, what are the capabilities it has, the protocol of communication using SPI, and what are the advantages and disadvantages of using SPI. So the serial peripheral interface, as the name implies, is basically a serial bus protocol. It was originally invented by the Motorola and later on adopted by many companies. It is very popular because of the simplicity of the protocol, because you just need 4 wires for communication between the microcontroller or FPGA and the peripherals. It is a very fast, easy to use and simple protocol, but however, there has not been a proper standardization of what should be the frequency of communication, or what is the whether it should be half duplex or full duplex, but normally we use it as a mode of full duplex communication. So, do you have any idea of half duplex, full duplex things? Okay. So, when two devices communicate with each other, so suppose this is the transmitter and this is the receiver, and you connect the transmitter and receiver by means of a wire. There can be two modes of communication between the transmitter and the receiver. If the communication is always unidirectional, that means the transmitter sends signals and the receiver only receives it, then that is called a simplex mode of communication. Simplex communication. So, it basically refers to unidirectional transfer of data. The second one is called the half duplex mode, but before that let us talk of duplex. If the signal transfer takes place in both directions, that means instead of this dedicated transmitter and receiver, I have what is called a transceiver. That means both the devices can have got the capability to transmit and receive data. Then that means both the devices have got the capability to transmit and receive data. That is called duplex mode of communication. Duplex communication mode has again got two forms. If the data transmission takes place in both directions, but at a particular instant of time it takes place only in one direction, that means when this device is acting as a transmitter, this will act as a receiver and vice versa. That means when this will act as a transmitter, this will only act as a receiver, and it will not transmit data until this device finishes transmission. And the opposite is true, when this device is acting as transmitter, it will only transmit data and this will only receive data and will not transmit until this device finishes transmission. Then that kind of communication mode is called half duplex communication. If the data transmission takes place between both the devices in either directions at the same instant of time, then it is called full duplex communication. No, I mean this is the main line for data communication. You can have other control lines also. So, yeah. So, if the transmission and reception takes place at two different frequencies, then it is possible to transmit and receive at the same instant of time. So, yeah, on a single wire. If you use two different wires for full duplex, then you can transmit and receive at the same frequency. So, that actually gives us the notion of two basic modes of communication. One is called baseband communication, and the other one is called broadband communication. So that gives us the notion of two types of communication. One is called the baseband communication, where you transmit signals at its basic frequency without undergoing any frequency shifts because of modulation, which you will learn in the next semester in communication theory. So, but then if you want to transmit data from different channels over the single communication channel, then you have to multiplex the data coming from multiple channels and allocate individual time slots to individual input channels by time division multiplexing, right. So, what is this time division multiplexing? Suppose 4 of them want to talk to me at the same time. I cannot listen to 4 of them together. So, what will I do? Suppose I make a policy that I will first hear Akash, then I will hear Prithvi, then I will hear Rohit, then I will hear Atharva, and again I will hear Akash. So, this is where I can do a scheduling between 4 of them, and I hear each of them in turns, which means I will hear all of them, but I will hear the each individual on a time shared basis. So, I am dividing my time into 4 time slots in which I am hearing each of them. So, that is the same principle that works in case of this baseband communication. So, multiple channels are sharing the multiple sources are sharing the same communication channel. Now, you have to time share between all of them. It can be on a round robin fashion, it can be on a priority basis, whatever that you have to choose. And then once you choose a source, you will transmit the data from that source to the communication channel. Okay. Yeah, I will come to that. So, this thing you followed. Now, suppose the question that he raised, Abhishek raised, that is, suppose I have just one wire, can I use the same wire for communication in both the directions at the same time? That is possible, provided these two devices transmit and receive at 2 different frequencies, so that there is no interference between the signals going in either direction. So, you recall your +2 knowledge of physical optics, where you studied about interference. So, what were the basic criteria for interference? Same source. The sources have to be coherent, right. What is the basic significance of saying that the sources are coherent? There should be a constant phase difference between the light waves emanating out of the 2 sources. That is why, since it is very difficult to ensure the coherence by having of 2 separate light sources, that is why we took a single light source behind the double slit and then have had 2 slits on the screen, and those 2 slits were acting as sources of secondary wavelets, if I go by Huygens principle, right. So, the base condition that we were satisfying is that the 2 secondary sources of wavelets, they had got a constant phase difference, and that constant phase difference was achieved by giving a constant path difference between those 2 secondary sources and the original light source. That is what we did in Young's double slit experiment, if you recall your +2 knowledge. What was the second criteria? The frequencies of the 2 sources, light sources, should be the same. So, interference will take place if and only if the frequencies of the light waves coming out of the 2 sources are same, otherwise you will not have that constructive and destructive interference patterns. Instead, you will the two sources will not interfere and just pass overlapping each other. So if we do not want the two signals coming from either direction to interfere with each other, one of the two things, one of the most important thing which we have to satisfy is that the signal transmission in either direction should be at two different frequencies, so that there is no interference between signals when they pass through each other, right. So if you are passing a signal in this direction, another signal in this direction, you have to ensure that this signal should not interfere with this signal, right. When you are passing a signal in this direction and another signal in this direction, they will pass through each other, but if there is an interference between the two signals, then it will lead to permanent loss of information from the signals. So I do not want the two signals to interfere with each other. They can pass through each other, but once they pass out, they should be same as before. So in that case, I should ensure that this signal should not interfere with this signal, and for that I have to ensure that the transmission of this signal and transmission of this signal takes place at two different frequencies. And since the transmission of the signals are taking place at two different frequencies, you can also generalize it to having n number of data sources or signal sources transmitting signals over the same communication channel at the same time, but in that case you have to divide the available bandwidth of the communication channel into multiple subbands and allocate them to the individual data sources or signal sources. So since you are using a channel with a considerable bandwidth and dividing the available bandwidth to the individual data sources or signal sources, so that kind of communication is called broadband communication. Since you are sharing the available bandwidth of the communication channel to multiple data sources or signal sources to facilitate transmission from multiple sources over the same communication channel at the same instant of time, therefore this mode of communication is called broadband communication. Okay. Yeah. So yeah. So that is why in communication theory you have to learn two things. One is called ISI and the other one is called ICI. I am coming to that. So this broadband communication you understood. So since I am dividing the available bandwidth of the communication channel to share between multiple sources, so what I am doing, I am basically doing a multiplexing of the available multiplexing of the frequencies of different signals, and that type of multiplexing is called frequency division multiplexing. Now as Rohan raised this question, that although our idealized expectation is that when we are transmitting the signals over a baseband communication system, we shouldn't expect the symbols or bits to overlap with each other, or when we are transmitting data from multiple sources over a broadband communication channel by doing frequency division multiplexing, we shouldn't expect interference between the adjacent communication channels. But in reality, some interference do take place because of the non-idealities in the characteristics of the channel, and that is why when two channels overlap with each other and they interfere with each other, that is called inter-channel interference or ICI. So, one of the figure of merit of a broadband communication channel, that means how good it is to ensure that what is the maximum amount of ICI taking place in the communication channel. Similarly, when you specify the characteristics of a baseband communication channel, one of the figure of merit of the baseband communication channel is what is the maximum amount of overlap between two adjacent symbols taking place when you are transmitting data from multiple symbols over the same channel. So, that is called inter-symbol interference or ISI. So, in telephones, you frequently, when you talk to another person over telephone, frequently you hear some other conversation taking place over the telephone, which is not your conversation, and we call it a crosstalk. The crosstalk is typically an outcome of this, is because of this ISI or inter-symbol interference. So, when the inter-symbol interference becomes considerable, you cannot intelligibly distinguish between your voice and the voice because of some other conversation taking place, and you hear the noise and the sound of the other conversation over your same channel.